let's talk about some basic principles of shaft-to-shaft alignment. In the image you see here, I have two shafts. The machine to our left is simulating the stationary machine. The machine to the right is simulating the movable machine. Often that's a motor. The blue dotted line represents the line to which I have to get the motor shaft to in order for these machines to be properly aligned. And you can see the further I go, because I have angular misalignment, the further I go away from the split of the coupling here, the greater the amount of misalignment I have. So as I go this way, I have more misalignment. So how do I correct that? In order to do that with this particular machine, I'm going to have to add a different amount of shim under the front and rear feet of the movable machine. To make that calculation, we might think about using trigonometry and equilateral triangles, or equal triangles rather, right angle triangles, and sines and cosines, but typically that would be very, very complicated. Of course, that's basically what our laser does. There is a much simpler way. Effectively, what I've got here is a slope. Okay? It's just a slope. And one way of defining slope is to define rise over run. And that's the definition of slope. Now, because this coupling is a perpendicular right angle, whatever the slope is here, it will be the same as the slope there. So this angle and that angle will be the same. So, if I was, for example, to take a gap gauge and I was to measure my coupling gap at the top here, and let's just say I measured that gap as 125 units, and I measure the gap at the bottom, and I measured that to be, say, 100 units, then my slope, my rise in this equation, which is the amount it goes up and down, would be the difference between those two numbers. So in this equation, rise would be 125 minus 50, minus 100. So now that would be my rise. If I measure the diameter of the coupling here, the point at which I use the gap gauges, and let's just for the sake of argument call that 5 inches, my slope then becomes rise over run, which is 125 minus 100, that's my rise, divided by my run, which is 5 inches. And when I do the math, that equals 25 divided by 5, which inevitably equals 5 mils, if we're using mils, per inch, or whatever the units are that you're using. That means that for every 1 inch I go this way, I come down 5 mils in this particular example. Once I have that slope organized, then all I have to do is measure the distance from the split of the coupling to the front feet, and we'll just make that a fictitious 10. And then the split of the bearing to of the coupling to the rear feet, and let's call that one 27. So if I need my front foot connection now, so if I look here, my front foot correction equals 5 mils per inch multiplied by the distance, which is 10 inches, equals 50 mils. And for my rear feet, if I take my 5 mils per inch, multiply by 27, we'll make the math really difficult, so that's 135 would be my correction to go in the rear feet. Put 50 in the front, 135 in the right, and you have now corrected your angular misalignment. Now, you'll still, of course, be left with an offset, but of course, I can always measure my offset with a straight edge across the coupling and do that. Now, I'm not suggesting we use straight edges and gap gauges to do our alignment. This is just about the principle. This is basically what the laser is doing. If you were able to follow this along as I went through it in your head, you can basically do alignment in your head.